There we go. Okay, I have pulled up a simulation called PopGen. I've posted the URL, and we're not going to use all of its functionality today, but what this lets you do is the simulation will do all of the mathematics for you much faster than you can with a calculator, and it will help you see what happens. Basically, okay, in the last problem that we worked, we looked at the change in allele frequency over one generation. We could have taken the numbers at the end of the problem and plugged them right back in and predicted our allele frequencies after a second generation. And then after a third and after a fourth, we could have kept doing this as long as we wanted to. Computers, of course, can do all of this automatically very quickly. So I want to show you a few things, and I might turn you loose to play on it. So we're on this web page for the simulator called Web PopGen. Over here at the top, I'm going to set a finite population. Over here, this says number of populations 5, and we'll do this for, we don't really need to do 400 generations, so I'm going to let it run for 100. Okay, down here, population size, this letter N, is set at 100. I'm going to make it a little bigger. I'm going to make it 1,000, because why not? And our frequency of, we have two alleles, and they're called A sub 1 and A sub 2. So I'm going to zoom in a little bit right there. So there's our number of populations, number of generations. Frequency of A sub 1 is 0.5, and I'm going to leave that there. The frequency of the other allele is the other allele is A sub 2, and the frequency of that is also 0.5 because, right, the two frequencies have to add up to 1. Over here, I've got fitness values for homozygous for A1, heterozygote, and homozygous for A2. Now, there's a couple of models we can use to simulate migration, mutation, inbreeding, and something called a genetic bottleneck. I'm not going to mess with that just yet, but let's start by having all of our fitnesses set to being equal. So I've set our population to be finite with a number of 1,000 individuals. The population's not going to increase or decrease. We're looking at 5 duplicate populations over the course of 100 generations. And when I click go, there's what we get. That's a graph of the change in the A1 allele frequency over time. And by the way, down here is the change in the A2 allele frequency over time. Since the frequency of allele A2 is always 1 minus the frequency of the allele A1, these two graphs are mirror images of each other. So if we look at this one, I'll zoom in a little bit. We started with our allele frequency of 0.5, and you can see that as time goes by, some of these have drifted away a little bit. That is a result of what we call genetic drift, and that results from random fluctuations in a population's allele frequencies based purely on chance. Remember, we said earlier that a population has to be infinite if it's truly going to be in Hardy-Weinberg equilibrium. Now, no population is ever truly infinite. This blue line right here, the thing right in the middle, that is the allele frequencies if we could have an infinite population. With a population of 1,000, you can see, that's not infinite, but you can see that these allele frequencies cluster pretty tightly around this imaginary infinite population line. So these 5 populations are close to being in Hardy-Weinberg. Okay, if I make the population even bigger, let's set it at 2,000, and I hit go. That's what I get right there. I think you can see the spread is even tighter. I mean, there's still some fluctuations there, and population 3 has gotten down quite a bit, just by dumb luck. If I set the population to 5,000 and hit go, see the spread is even tighter. If I set it to 10,000 and hit go, there, right there, those lines are just getting closer and closer to the middle. So with no selection and a really large population, um, over 100 generations, the allele frequencies stay very close to Hardy-Weinberg equilibrium. On the other hand, if I make the population a lot smaller, let's say I make it a population of 100 and I hit go, now I've got a lot more zigging and zagging. In a really small population, random factors start playing a much bigger role. Here's the example I always give. Let's take the population of Little Rock. I'm not even sure what it is, but I think for the city itself, it's something on the order of 300,000. Okay, close enough. Okay, every day people are born in Little Rock, and every day people die in Little Rock. And these roughly balance each other out. Now, human eye color is actually controlled by multiple genes, but roughly brown is dominant to blue. So I could go around Little Rock and I could, estimate the number of brown-eyed people and blue-eyed people. I could take a survey at, McCain Mall, or well, that's North Little Rock, but no matter. I could take a survey at wherever people in Little Rock are gathering, and I could estimate the number of blue-eyed and brown-eyed people, and maybe I could estimate the frequency of blue-eyed and brown-eyed alleles in Little Rock. Okay, if one person who is blue-eyed in Little Rock has 14 kids, that's not going to change the allele frequency very much. If one blue-eyed person in Little Rock happens to step out right in front of a Central Arkansas Transit bus and get killed, that's not going to have very much effect, not in a population of something like 300,000 people. On the other hand, a few years back, I drove up Arkansas 7 north of Russellville, and there was this little, looked like mostly a tourist trap, but there was this tiny town called Booger Hollow. And they had a sign, population 7, counting 1 coon dog. Now, the coon dog should not be part of the human breeding population. Let us hope, because ew. So let's say there's 6 people living in Booger Hollow, Arkansas, on scenic Arkansas Highway 7, a piece north of Russellville. Your last chance for cheap souvenirs before Dogpatch, except none of you remember Dogpatch. Okay, so there's 6 people. Now, I could go up and interview those 6 people in Booger Hollow, Arkansas, and some number of them have brown eyes and some number have blue eyes. So I could estimate or calculate the allele frequencies there. If one blue-eyed person in Booger Hollow happens to step in front of an out-of-control 18-wheeler on some of those rather steep slopes on Highway 7, that's going to have a very big effect, a proportionally much greater effect. So the smaller your population gets, if I take it down to 20, scatters all over the map. Allele frequencies just go randomly zigging and zagging every which way, except once an allele frequency reaches 1, it can't change anymore, right? Because that means that A1 is the only allele present and there is no allele A2. So no further change is possible. And we say that that allele has been fixed. Or in this case, when A1 goes to 0, A2 is the only allele that there is. No further change is possible, and the A1 allele has been lost. So in this case, after 100 generations, in one population, A1 was fixed. In 3 of them, A1 was lost, and there's only um, one population that still has both A1 and A2. And that one, the allele frequencies have been zigzagging at random, um, from very low to very, very high. So that's what genetic drift looks like. I'm going to take the population size back up a piece. Let's set it at 10,000. And let's see what we want to do with fitness. Let's say we assign the A1 genotype a fitness of 1, and the A1 A2 genotype a fitness of 1, and the A2 genotype a fitness of 0.5. That means that if you have the A2 genotype relative to everybody else in the population, your chances of reproducing successfully are only half as good. And if I hit go, that's what I get. The frequency of the A1 allele rises and rises and rises and gets very, very, very close to 1. Ta-da! On the other hand, if I do it the opposite way, I set the fitness of the A1 genotype to 0.5, meaning if you have this genotype, you only have half as good a probability of reproducing relative to the others. And I hit go. Well, I get that. In fact, what I get there is kind of the mirror image. Notice, by the way, that at the beginning, the frequency of A1 goes way down pretty quickly, but it tapers off and it asymptotically approaches 0, but doesn't actually reach it. This is part of the reason why we still have rare alleles in the population with very negative effects. You might be wondering, if selection works, why do we still have alleles for cystic fibrosis and Tay-Sachs syndrome and muscular dystrophy and all of these things that would be strongly selected against? And the reason is that natural selection is not that good at getting rid of alleles that are already extremely rare, because those curves will asymptotically approach 0, but it takes an extremely long, well, in an infinite population, it would never quite reach 0. That's the definition of asymptotic. In a finite population, there's always a chance that genetic drift will knock out a very rare allele, but it may take a very long time for that to happen. So that's part of your reason as to why we still have alleles present in a population with very negative effects on survival and reproduction. Natural selection is not that good at getting rid of extremely rare alleles. Incidentally, neither is eugenics. Right. Let me see. So that's basically how you work this. I'll tell you what, I want to introduce a concept, and I'm going to go ahead and stop recording and just have us play with this for a little bit. So the recording is stopped right now.